thank you. So first of all, maybe I should start. Are there any the kind of questions from the previous two days? All right, then. So for today, the topic is going to be infinite stuff. So pretty much, if you open any textbook on probability theory, they're soon going to start talking about let xn be a sequence of random variables, then something, right? So it's about infinite sequences. And so certainly that means if we want to claim to have a kind of reasonably complete approach to probability theory in this abstract setting, then we need to be able to reproduce that and to deal with these infinite sequences of, well, with random variables, which in our settings translates into infinite sequences of objects. I mean, we kind of don't work with random variables very much in any case, but just with their distributions, which is kind of amounts to basically the same thing. So at the level of distributions, we would be talking about a probability measure on an infinite product space, right? I don't know if the random variables are real valued, then the giant distribution of a sequence of them is a probability measure on the infinite power r to the n, right? And so this is something for which we need to have a categorical description as well, and so the Markov category setting before we can then try to formulate things like the law of large numbers and the Diffie-Hellman theorem. Okay, so how do we do this? Well, how do we even talk about finite products to start with? Well, that we know, right? There we have our tensor products, the monoidal structure on the category. We can take like R tensor R, it's just R2, and so on. So for finite things, we're good. And now we kind of need to basically take the limit as the power goes to infinity. And this is going to be the following definition formalized in the definition of what's called a Kolmogorov, what we call a Kolmogorov product. Okay, so that means we start with a sequence of objects in our category. So think of these as measurable spaces, if you want, or again, commutatives used to algebras, of course. And then what we want to define is a sort of infinite product. So I'm gonna denote this infinite product like this, and where the tensor indicates that it doesn't have, well, you could also use the product symbol for this if you want to. Just for category theorists, this may be a little misleading because it's not categorical product in our Markov category. So that's why I write it with a tensor symbol instead of a product symbol, as we generally do in our Markov categories. Okay, so now what is the actual definition? And well, since this is a categorical definition, it's a universal property. So the defining characteristic of this product is going to be a kind of bijection between morphisms with various kinds. And in this case, we're defining what morphisms into this object correspond to. So if we start with a simple case, let's say morphisms from our singleton, which is the unit of our tensor product, these are into an object X. Well, in Perel-Stock, for example, these are the probability measures. In a C-star case, they are our states. So if we now map into this, we're looking at probability measures. So in the case of Railstock, looking at probability measures on an infinite product. How do you think we can approach these? How does one deal with probability measures on an infinite carnival product space?
Kind of sequences of probability measures on the
Yeah.
part. Also, can I ask why is it obvious that in Borel stock this maps of this form correspond to probability measure?
That's something that I really should have explained on Monday, I guess. So when we just have this is going to be a singleton set, right, or a singleton measurable space, and a Markov kernel like this, it has only one possible input value, right? So it's like a function that can only take one possible input value. It's just an element of the target. And in this case, Markov kernel correspondingly is just a single probability measure on the target. Okay, and then so defining bijection is exactly that. And now I extend it to Markov kernels and kind of the same idea holds. To define a Markov kernel into an infinite product, well, we define it's enough to specify its finite marginals, as long as these are a kind of consistent or compatible family. Okay, so we have a defining bijection that again I'll draw with this kind of horizontal line. So the morphisms, Markov kernels from A into this are in bijection with compatible families of morphisms into the finite products. And in a categorical language, these are certain kinds of entire diagrams. Right, so the looking at the finite products means that we look at just a morphism or a Markov kernel into x1, then into x1 tensor x2, into x1 tensor x2 tensor x3, and so on. So if we start here, we can just marginalize, or that's at least in the case of Borel stock, this is what it means. We can just project, marginalize onto the first n components. Then we got a Markov kernel like this. And if we project onto n-1 components, we got a Markov kernel like this, and then the corresponding triangle here commutes, because the projection of a projection is just the projection. Okay, so yeah, I'm leaving a little space here because there's going to be two extra conditions. So the definition is not quite complete yet, but I just want to note, for example.
Sorry, but yes.
Yeah.
It's important the order, so it's 1, 2, 3, or could be any separate.
No, it's actually not. So it's just let's say you can order it in whatever way you want. And actually, what I'm presenting here is just special case of the definition where we're looking at countable products. We also have a definition for any family of objects, and then instead of looking at finite marginals as ordered like this, we just actually look at all the finite subsets, finite subproducts, so to speak. But So this is a kind of simplified version of the definition, and the general definition doesn't have any ordering.
And what are the connecting maps? And is it just any map between?
No, these are so the obvious projections are these.
But it's not, the tensor product is not in general the categorical product, is it?
No, it's not. But yeah. So right. This one, for example, is you basically just discard. So these maps are defined in terms of the deletion or deletions. On the other hand, you could say at a level of the deterministic subcategory, there the tensor product, as I mentioned yesterday, the tensor product is the categorical product, and there these are the actual projections, product projections. Okay, so Kolmogorov products are these. So yeah, these. When I say Kolmogorov products now, I mean these countable Kolmogorov products, since I haven't introduced the general definition. But when you write it in papers, Kolmogorov product would mean the general one that need not be countable. So they exist in Borel stock. And they're actually given by the product of measurable spaces.
The definition of Kolmogorov product makes sense on a copy discard category.
Yes, it makes sense, but there's a certain, I think in general, CD categories, it's not so well behaved. And basically because if you measure and take the CD category, where you drop the normalization condition on the Markov kernels, and then you kind of run into kind of potential. But yeah.
But not all Markov category. So let's say we take normalization in consideration, which I think is reasonable for infinite tensor products. Does a Markov category have a Kolmogorov product in general?
No. I mean, thin stock, for example, because we just have finite sets, clearly does not have Kolmogorov products. So some of them do, some of them do not. The fact that you have infinite objects, so if you just take, let's say, we can take standard Borel spaces again, measurable spaces as objects, but just take Markov kernels that are finite, where the distributions have finite support, so atomic finite support, then it will fail purely. So it always depends. Yeah.
You know about stock, Borel stock?
Countable ones, yes. Uncountable ones, I don't think so. And so this has to do with I couldn't produce a counterexample right now, but this is kind of these are old measure theoretic counterexamples. So the reason that it works with Borel stock and also countable, I think countable ones in stock, but actually I'm not totally sure about that right now. But in Borel stock, yes. And I was going to write down. So here it's just a usual product of measurable spaces, and the fact that this property holds, at least for probability measures, that is known. That's called a Kolmogorov extension theorem. That when you have a probability measure defined on finite products, that it uniquely extends to a probability measure in the infinite product, that is basically a Kolmogorov extension theorem for one version of it.
In this case, it would be the projective limit in the sense of the value.
Right, yeah. Mm-hmm. Okay, what about now our commutative C-star algebra example? Well, there we kind of need to read this the other way. And then, yeah, I think Fabio already realized that yes, they exist as well, and these are basically the usual. If you've seen infinite tensor product C-star algebras, unital C-star algebras before, this is exactly then what it is. Okay, but no, I haven't actually quite finished the definition here yet. As I said, there's some additional conditions. And so maybe I can just mention these, but they're kind of technically important, but now conceptually maybe not so relevant. But so one thing that we clearly want is that if this thing is deterministic, so if this is a measurable, let's say Borel-Stock, an actual measurable function, then so should all of these ones be, and vice versa. That's just maybe something that you've already kind of automatically assumed, but it's not. I mean, we need to impose it as an additional condition since it's not encoded in here already. So this bijection restricts to a bijection on deterministic morphisms. And one more thing that we need, or that we want and frequently use, is that this bijection is additionally preserved by adding one more object to the sequence. So if I take all of this tensor some object y, then the whole thing still holds. I don't know I wouldn't actually know of any example where this would hold, but this extra preservation condition would not. So it's kind of, in practice, this tends to be the case. Okay, so now when we look at sequences in the context of the law of large numbers and so on, there our sequences tend to be such that it's all the same object, constant sequence. Like for real valued random variables, it's always R. Right? So in fact, this is a kind of special case of Kolmogorov products, and we call these then Kolmogorov powers sometimes. And I just want to introduce a notation for these. Kolmogorov power to well, then maybe a slightly abusive notation, which then looks more like a product, but then for these Kolmogorov powers, we just write x to the n. And so this is, yeah, the Kolmogorov product of x, an object x with itself infinitely many times. So maybe I can write it as just nx. Okay, so now we can turn to stating the Definetti theorem, which is maybe finally the real first actual theorem that I can present and that we've proven in terms of this machinery. And so what this is concerned with is exchangeable morphisms. Maybe I should actually ask who has worked with or at least seen the Definetti theorem before in whatever form, quantum Definetti theorem. Okay, not so many. Yeah, good. That's good enough. Okay. So, well, in probability theory, we often talk about IID things, right? Like the law of large numbers. We average values of IID random variables. And obviously these have a nice symmetry. In a sense, and you can permute them and you still, the distribution is still the same. Now imagine we have a situation where we don't know what the distribution is. Let's say we know that we have a coin where we don't know if it's fair or an unfair coin, but we can flip it any number of times. Well, then, because we don't know what a bias is, look at our belief of what the sequence of outcomes we're going to get, it's not going to be IID because it's not going to be independent. And maybe because it's sort of correlated through our belief on what the bias is. If we think that a coin is fair, well, then we have the sort of sequence of an IID sequence. If we think that it's another bias, it's another IID sequence, and overall the distribution is is a mixture of these, right? And that makes it no longer IID. Or you can also put it like this: if it's not IID because learning the outcomes of the first few flips will help you estimate the later ones. Right? Because then you know, well, you can guess, well, okay, this coin kind of looks biased. And so I'm going to guess that the future outcomes are going to be more like the ones that I've already seen.
So somehow you are incorporating yourself in the distribution, so to speak.
Yes,
if
exactly.
The true distribution, that's completely, the fact that it's IID or not doesn't depend on you.
So if you model your belief about any sort of repeated experiment, then you're very much in this Definetti territory.
So you need to model your belief inside the Markov category, so to speak. So it's like you have two distributions, right? The distribution of the coin and the distribution of your belief, whatever this may mean.
So just right. I mean, this applies both to the ordinary formulation of probability and to the Markov categorical one. Everything that we're doing can model sort of physical processes, can model beliefs. It's always, and maybe other things too, but at least these two kind of dual things are always are things that appear and that we want to work with. And so maybe we need to be a little bit careful with the string diagrams also. Maybe it's tempting to think of these as always some kind of physical things that happen, but that's not the case. And so often these things, especially in relation to conditioning and so on, you want to kind of model beliefs and still draw them as these kinds of diagrams that where we can see kind of information flow and is maybe tempted to think of it in physical terms.
Basically, you are looking at the sequences of estimators and how they are, as a process, a random process, how this random process is independent, Markov or not, basically.
Yeah, this one can do that, right, yeah. This already kind of goes further than what I want to talk about, but yeah. Okay, so this at least motivates the definition that the kind of probability distributions then that we're looking at are probability distributions on an infinite product. And they're not necessarily IID, but they still have this permutation symmetry. Okay, and so this is what this concept of exchangeability, it's called exchangeability, is about. And the Definetti theorem will characterize these. So now this works in a general Markov category with Kolmogorov products. So yeah, amorphism P, and now I'm writing P to kind of suggest, indicate the kind of probability measure interpretation is exchangeable. It is invariant under finite permutation. Meaning that I look at P, and so I'm going to draw this with sort of infinitely, I mean, technically this has infinitely many output wires, just as dots. And now if I permute these, if I permute finitely many of these, let's say if I just permute the first two, then it should still be the same morphism, still P. Right, and so now, yeah, as an example, keep maybe this coin example in mind, a coin where we don't know what the bias is, and want to model our belief about a sequence of tosses. Okay, so now here's the Definetti theorem. And I can maybe formulate our categorical, or well, we have several kind of categorical versions of it by now, but our original one was that, so if we're in a Markov category as Kolmogorov products, conditionals, and is representable, if you recall the kind of this distribution objects and representability from yesterday, then we need this in a slightly stronger form that we call that I haven't introduced, and maybe would be going a little too far right now. It's just a minor strengthening of representability that we call AS compatibly representable. So it's basically representable in a way that's compatible with almost sure equality. Then every P that is exchangeable can be written in a form that corresponds to a coin with an unknown bias.
Known bias or unknown bias?
An unknown bias. And so formally, for every exchangeable P, there is a mu. Oh, or I should write the just for completeness. So the P is still is as above a x to n. There is mu a to px such that the P has the specific form namely I can write the P as mu, and mu is basically the distribution over the biases. And then I basically copy infinitely many times, and from each copy I'm going to sample. Sorry, this is going to be hard to read, but yeah. So this is mu, and we copy here, and then sample from each copy. And so in the coin example, X would be just a 2-element set, corresponding possible outcomes, heads or tails. Then Px is the probability measures on that set, meaning the possible bias values for the coin. And then mu would be a probability measure on that. And so that's our belief about the possible biases.
You are introducing the concept of heuristic distribution. Basically, doing the sampling, you get a distribution from the sampling, and you are estimating the parameter from.
Not yet. And we don't actually need that concept for the proof, but that's exactly the concept that we're going to get to next. I mean, here we're not looking at any sort of heuristic. We're not looking at that explicitly here. But it's definitely closely related.
So here, in this second diagram, the arrows are, you go mu to px, and then you copy it infinitely many times. That is like taking px to the end, the common product, or...
Yes, that's right. Yeah. Thanks. That's a good point. So here, this is px to the n. And so and intuitively that means we take then this random coin, we take one of these, which is distributed according to our belief, and then we've tossed this coin infinitely many times. That's what the sampling does. And then so the right-hand side is precisely what I had how I had motivated exchangeability in the first place, right? Through the unknown bias example. And so De Finetti's theorem says that this is actually the general case. All exchangeable distributions and Markov kernels look like this. Okay, this is also a kind of there's other theorems along these lines, and so one of our most recent results is a kind of extension to this, to the case where you have not a sequence, permutation invariant sequence of random variables or distribution like this, but an entire matrix, and that is invariant under exchanging, swapping rows and columns. And there's an analogous, so this is related to random graphs, and a similar kind of theorem. Like
You can use nets instead of sequence, and you can consider the number of products for nets in general.
That's right, exactly, yeah.
And then the symmetry is connected to some symmetry of the graph, so over which you are this exchangeability is connected to some sort of symmetry of the graph.
Pretty much, yeah. So it's about it's roughly about symmetric random graphs. And you can basically, I mean, identify a graph with its incidence matrix. And then if it's random, you basically have for every edge a random variable that tells you whether the edge is there or not. And the random graph is symmetric if basically it's invariant under permuting the distribution is invariant under permuting the vertices. And this amounts to permuting rows and columns of the matrix. No, that's an important point. This mu, I mean, so in the current example, it's still a distribution over the biases, right? So if you want, it's an element of ppx.
So
Yeah,
we are
so
not using the identification you were mentioning yesterday about kernels and
exactly, yes,
that's
yes.
something different.
So if you write it as a deterministic morphism, it's mu sharp from A to ppx. So you can think of it as a measure on measures. And then people often call this a random measure. And this is one of the strengths also of the categorical formalism. Here we can iterate the P as many times as we want when we have a good language for dealing with this. And working with distributions on distributions on distributions.
How does this translate to the sister algebra case?
It
doesn't.
Yes, it does.
It does?
Yes. There is a quantum definite theorem.
No. Sorry, it was not precise. The thing of iterating of going to the P of Px.
Oh, I see. Yes, yeah, that generalizes this as well. Yeah. I mean, the P, there are, in the quantum case, and I can talk more about that tomorrow, there are two versions of the P. There's a genuine quantum P and then the classical P. The classical P I had presented yesterday as the continuous functions on the state space. And I don't know if you'd be interested in iterating that, but at least one can iterate it. You just can apply it again, right? So it's an endofunctor. You got a C-star algebra again, a commutative one. And you can iterate the construction.
Yeah, but then you lose the suppose you have an algebra,
right.
you lose it immediately at the first iteration.
Yeah. But the quantum version of this key that I can talk about tomorrow, in that case you don't. Okay.
Is this mu unique?
Yes, it is. I'm not sure well, so we have not proven the uniqueness. This is maybe a bit annoying that in a general categorical theorem, we have not been able to prove the uniqueness from our assumptions so far. But in Borel-Stock, where the theorem is true and our proof applies, the uniqueness turns out to hold.
Do you believe it's actually like limiting on more general case of Markov categories with Kolmogorov products, conditionals, and
Yeah, I'm not sure. If the assumptions I stated here would be enough to prove the uniqueness, no idea. Yeah, I mean plausible, but
Because then we would have a one-to-one correspondence between these exchangeable morphisms and.
so this can be used, and if there's enough time, I can still get to that. Can be used to characterize, give another kind of definition of the PX, another universal property for PX. Maybe this is, I think this is probably the direction you're going into. Yeah. If we have enough time, I'll write that down. Okay. So then, for now, I would table this and get back to the direction that Fabio had mentioned of looking at a sequence and its empirical distribution and trying to kind of turn that into a distribution from, what is that the sequence kind of been sampled from.
You're trying to look at that in the sense of Bayesian inference.
I want to look at it kind of independently of that context. But yeah, I mean, one can definitely use it in that setting. But I just want to look at it more abstractly and as some,
Because I don't know if this form seems to remind me of a prior and some posterior.
Yeah.
Describe the vision in this sense.
Yes, that's a good way to think about it, and also kind of ideas that we use in the proof to basically look at the tail conditional, which is if you already observe an infinite subsequence, what do you think the next outcome is going to be? So this is a conditional. And working with that conditional is then how we prove this, or let's say what we use in the proof. Okay, but let me actually start a little differently. So this is the Finetti theorem, and now I'm going to talk about law of large numbers. And they're actually kind of closely related, and I think Fabio's thinking is exactly also hinting at that relation. But let me write it down first. And then let's talk about how one might formulate that in category of theoretical terms. So this is considered a strong, I mean, there's many different laws of large numbers, but let's consider the Commodore's strong law of large numbers. And well, maybe actually to not make this confusing, let me now write random variables as lowercase, since my uppercase letters denote objects in the category. Okay, so then what we have is an IID sequence of real valued random variables, right? Then with finite first moment. Right, they shouldn't be too large with high probability. Then, if we look at the empirical average, look at the average value of the first n. So this is what we might observe in an experiment. But then the idea being that this average gives us a good indication of the actual expectation value. We don't know the underlying distribution, so we can't compute the expectation value, but we kind of try to estimate it by having these n samples, and we hope that this is sort of close to the actual expectation value. And welcome with the strong law of large numbers tells us a sense in which this is actually the case, because at least this converges to the expectation value, almost surely. Okay, yeah, so keep in mind that the xi are kind of random. So the left-hand side is a random quantity, and in particular, the statement, part of the statement is that the limit exists with probability 1. And is then basically constant and equal to the expectation value. Okay, so does this look anything like Markov categories? Not much, right? It looks very, very different to start with. So I guess one reason being that we're taking these averages here. This is something arithmetical. And I've given no indication so far, at least, of how to talk about anything like that in categorical terms. And I'll get to that. But for now, let's maybe simplify our lives a little by formulating a different theorem, an actual harder, or a different kind of law of large numbers, which does not require us to do this kind of averaging. Namely, what I want to do is to say that, well, why are we just looking at these averages and looking at the expectation value? If we look at the sequence, our samples x1 to xn, there's really more information in there. Right? There's information about the variance. We can look at, well, the entire, how are these n first samples distributed? We can maybe draw some kind of histogram. And then maybe we would expect or hope that for large n, the resulting histogram approximates the underlying distribution.
That is Kolmogorov's theorem.
Kolmogorov's what?
Kolmogorov Smirnov theorem. No? That the empirical distribution approximates the distribution enormous probability.
To be honest, I forgot what exactly Kolmogorov's Smirnov theorem says, but there is the version that we've been working with is the Klavenko-Cantelli theorem, which is also a statement of that type. And maybe I don't want to go into these kind of very technical details now, but just to kind of sketch the idea. So what we can translate in Markov categories a bit more easily than this is this sort of theorem Klavenko-Cantelli or Kolmogorov-Smirnov. And I want to make this a little informal now. That not just do the expectation, these averages converge to the expectation value, but the entire distribution converges. And so when we're looking at the distribution, well, we're looking at probability measure, and maybe we can write like this. right? This would be kind of the empirical distribution of the first n samples. And then these theorems provide a sense in which the same statement holds. And maybe I'll put this, oh, sorry. Yeah, but then this is equal to the underlying distribution. And so maybe I should introduce a name for this distribution. So let's say if the xi's are distributed according to some distribution mu, then this limit is mu again, and again almost surely, so with probability 1. If this is, again, here we're in the territory of random measures. So this is an element, for every sequence, this is an element of px. But now the sequence itself is random, so it's an element of ppx, really. Okay, so yeah, still in this IID setting, if these are distributed according to mu, then this holds almost surely. Okay, and there's many subtleties kind of hidden in this notion of limit here, that that there are various theorems that make this concept of limit precise in different ways. And so, for example, for the Klivenko-Cantelli theorem that we've mostly been considering, the statement is that the cumulative distribution function on the left-hand side uniformly converges to the one of mu. And then I guess the Kolmogorov-Smirnov theorem is something a little different.
Yeah, maybe it gives you the distribution of the difference between any unit and the distribution, and the empirical one is a random variable which has a certain distribution. So
Yeah.
maybe the Kolmogorov-Smirnov. So that,
Look, here you are seeing the distributing object as a monad in order to see a distribution, the ppx, and a distribution in the distribution space as just a distribution in this space. Here you are mapping from ppx to px. One of the parts of the statement.
No, not exactly. So this is more. This is both sides here really are in ppx if you want if you formulate it like that, and then the right hand side is basically delta at mu, right? Because the point is that it converges to mu with probability 1. So it's really concentration of measure to mu.
Is that also related with Fritz representation theorem, because you are defining this sequence of measures on the left that turn up to converge in the end to a measure? I mean,
Yeah.
so the difference between these theorems is the topology that you end up putting on the both sides.
We've been trying to let's say do a version of this for compact Hausdorff spaces in terms of Fritz representation theorem, but haven't really have run into some technical issues, so we haven't really gotten that to work. So, but with the Klivenko-Cantelli version, it's not about the Fritz representation theorem, since I mean R is not even compact, so we can't quite use that. All right, so this is the measure theoretic version. Or at least the informal measure theoretic version. And now, again, the question would be, well, how do we formulate this in categorical terms? And again, it does not look so far much like maybe this doesn't quite look as bad as this, but still not something that, let's say, a Markov category natively supports. It doesn't have enough structure to talk about this. And now, well, also concerning the limit is not something that we have, and maybe one can do something along the lines of what Paolo had been talking about on Monday, with some kind of topological metric enrichment, and then make sense of the limit in those terms. But what we've done now is something a little different, and I think results in something a little even kind of more higher level, in the sense that we've basically formalized or axiomatized the entire left-hand side. So, I mean, if you follow a kind of topological enrichment approach, then you still have to make sense of this thing. So then you kind of have to make sense of this average and the limit separately. But what we've done now is to make sense of the left-hand side jointly as its own categorical structure. Okay, and so if we look at what the left-hand side is, well, so roughly speaking, it's a construction that takes an infinite sequence and would output a probability measure. If let's say if suitable conversions holds. Yeah, so roughly what we would want would be a kind of map like this. Along the lines of what Fabio had mentioned earlier, basically. Take an infinite sequence and then associate to it an empirical distribution. That would be the limit of kind of these finite empirical distributions. Okay, and clearly this cannot always be defined. I mean, the limit does not always exist. So it's really just a partial map. So a partially defined map. And so maybe let me introduce this kind of half arrow notation for partially defined maps. Okay, but so in our Markov category setting, it's a little more natural to not consider maps that land in Px, but to directly work with the corresponding Markov kernels. Right, to say that instead of mapping from x to the n into probability measures in x, well, in our setting, it's the same thing as a Markov kernel. So now it would be like that, and I'm going to erase the p. And what I want to construct is a Markov kernel like this that takes an infinite sequence as input and produces a random element of x as output. And what we call this is empirical sampling. So it would basically amount to sampling from the empirical distribution, empirical sampling morphism. Or okay, let me actually now write down our abstract definition. So now I've been kind of mostly talking about the measure theoretic setting, but now I want to write down our axioms, Markov categorical axioms, for when a morphism counts as an empirical sampling thing like this. Okay, so an empirical sampling morphism is a partial morphism, first of all, but maybe I don't want to talk too much about this this part here, and unless someone wants to know more details about what a partial morphism is, I think I will just sweep this under the rug and claim that this can be made sense of. Well, and so we have two conditions on this. One is it should be invariant on the finite permutations of the input sequence. And this is, I guess, kind of both apparent from here and intuitive, that if you just swap the first n elements in some way, the empirical distribution does not change. So it's important as finite permutations only. If I have an infinite permutation and I somehow rearrange the entire sequence, then certainly the relative frequencies of how often some element appears can change. That will change the empirical distribution. That's finite sequences, finite permutations.
You will use a diagrammatic notation like previously, or
No. Oh well, I mean the string diagrammatically, yes, but it's not. Yeah. So what I wanted to say next is it's not exchangeability, because this is at the level of outputs, but here we have the permutation variance for the inputs.
Like co-extendibility.
Yeah. Yeah. Mm. Okay. And the second condition. Now it's related to exchangeability again, and says that if f if we have any exchangeable morphism, and let me maybe first write it down first, and then we can see if we can gain some intuition for it. So suppose that this is exchangeable invariant on the finite permutations here in these x outputs. Okay, let me just actually use the notation that we use. So when I draw a double wire now, this means that this stands for the Kolmogorov power. A double wire is kind of a stronger wire, so this is the whole sequence lives on here. And now what I want to do is that I want to copy the sequence itself infinitely many times and feed it into this empirical sampling morphism. Yeah, sorry, this is a little cramped. But yeah, so what I'm doing is that copying sequence infinitely many times, and for each copy, do an empirical sampling again. And now the condition says that this is f again. F is invariant under this kind of resampling.
The copy is compatible with the limits that you are taking, and all the structs, the copying is everything compatible with the interchangeable with the limits.
You mean the Kolmogorov product?
Or not always.
What do you mean by compatible exactly?
Interchangeable, so we can move the copy before the limits. Or
Which limits?
in this the product, the Kolmogorov product.
I'm not sure what exactly that would.
No.
Yeah, okay. I mean, this Kolmogorov, this copy is, you can itself define it, or it's basically characterized through the universal property of the Kolmogorov product as well. In the sense that if you marginalize to a finite subproduct, then it's exactly basically the copy on the finite subproduct. I guess this is what you're getting at, right? Yeah, okay. Okay. Yeah, so if we have an exchangeable distribution, or for example, imagine that we have an IID, we do again infinitely many coin tosses, and do apply this empirical sampling. Then what this tells us is that then we get another infinite sequence of coin tosses, but it's the same distribution.
If you just took a finite number of measurements, then this wouldn't be true, right? Because
exactly, yeah. And this is so I think this is one of the advantages of combining the limit and this thing into one thing. That here we get an elegant abstract axiomatization that is actually quite powerful. So think of this process of infinitely copying the sequence infinitely many times and applying this empirical sampling to each of them. Think of this as a kind of resampling. Or at least that's how I think about it. And actually, if you take this if you make this precise, which is what we've done for standard Borel spaces, then one can actually prove that this resampling amounts to taking the original sequence and applying a random permutation to it. So instead of taking the empirical, there's two equivalent descriptions of it. One is you form the empirical distribution and then draw repeatedly sample from that again. Or you take the input sequence and randomly permute it. Maybe it's a little counterintuitive at first.
When you say permuted, you mean permuted, but just find a number of elements.
It's basically take the limit over finite. So it's essentially permuted, apply a random finite permutation to it, and then take the limit over the size of the permutations, and then this corresponds to this limit. And the two limits exist in exactly the same cases. So yeah, basically then what we've done is to show that in Borel stock, empirical sampling morphisms exist. I mean, we have precise constructions.
In this sense, you cannot see that this is the average. Could be any mean in principle. You have only a morphism that connects. So in principle, it's not doesn't need to be a sum.
Right. Yeah. Actually, I mean, this, as long as it satisfies, there's at least superficially nothing about averaging in here, and maybe one can have completely different constructions. I don't know. This is completely open so far.
But because
so far, also Borel stock is the only category so far where we have any empirical sampling morphisms. We don't. I mean, I feel like there probably aren't many others. It kind of feels like it characterizes measure theoretic probability, or might go in the direction of kind of being unique in some sense, maybe to measure theoretic probability. But it's conceivable that they're completely different constructions just
To find that you need real value things, you need numbers. But random processes, you can pick balls
Well,
of different colors. How would you define this?
I mean, for this, we don't. Maybe we don't need real numbers for this.
That's the point.
But yeah, and that's so far. Yeah, really not
Yeah,
much. It's widely
Balls
speculative.
of different colors, and you have an infinite supply of them. Then this averaging, how would you average the different colors to get? So this doesn't make sense at all. But
What do you mean by colors?
you have a sample of colors, blue, red, white, for instance, and you have them all in infinite number of balls that are mixed with a different amounts. So you're randomly picking them out of the ball. Mapping that into numbers is hard, but this would make sense in your setting.
Well, we still. I mean, this we do have empirical sampling morphisms for when X is a finite set.
No, I mean, suppose that you have an infinite supply of balls, and then this is the case because you can take the balls, you can take a countable number of balls out,
Yeah.
but averaging the colors doesn't make sense at all. So you couldn't fit that problem into there.
Well, so this doesn't make sense. Yeah, but this still does. Right? Or so the empirical distribution exists, or well,
yeah.
it may or may not exist depending on what your sequence is, but it makes sense to talk about its existence. What are the relative frequencies of the individual colors? That's the real number, and that's what we're looking at.
Yeah.
In the case of Borel-Stock, when X is a finite set of colors. Okay, so yeah, let me just note this down on theorem. Empirical sampling morphisms exist on Borel-Stock. And maybe you can see that this has now a kind of a flavor of the law of large numbers. It's kind of in the IID case. So if F is just IID, and then you're doing this free resampling, that reproduces the original distribution. Has maybe some similarity with this statement. So in a sense, we're kind of using something like a law of large numbers now as an axiom. As an axiom at a categorical level, and we've proven that this axiom holds in measure theoretic probability. And this was actually quite difficult. And this, yeah, this involves some kind of first of all, the characterization in terms of the averaging over the finite permutations. And yeah, there's some kind of partly analysis involved. There's maybe probably the most difficult, at least, measure theoretic stuff that we've done so far.
Sorry, just one question. This invariance and the is to be connected with the distribution of the first arrived, the second arrived, the third sample, the nth sample that are invariant under permutation this distribution.
Mm-hmm.
We are going to this, and so in this sense, when you go to the results, you have a uniform distribution always, and from the uniform distribution you recover the initial distribution. So from the empirical, so you have that the result, a possible result, extracted result, in the possible values of the random variable, you extract them uniformly, and then you recover from the empirical distribution, yes, the original distribution. So it's something here, the fact that you have the axis, you are sampling from this possible sampling. I don't know, it reminds me of this possibility that you have a uniform something, and then from this empirical sampling of this uniform distribution, then you recover the cumulative distribution. So this is the strategy that is behind So it could be interpreted in this way.
Yes, yes. I mean, that's sort of. I think I haven't quite understood everything that you said, but it sounds very similar to this statement.
Yeah. It's the. I think that was the state.
Yeah. Okay. Right. Then yes. I mean, this axiom is maybe vaguely similar, but different. But then one of the things that I mean, we have a lot of things that we derive using this as an axiom. There's a lot of other things that we derive from it, and I'm going to write down then a sort of categorical version of that statement.
So it derives from this.
Yeah. Right. So, okay. What about the C star case? Maybe this is interesting to look at as well. And there, I don't know yet. And I feel like probably C star algebras, now we're kind of probably hitting the limits, the limitations of the C star algebra framework, in the sense that now I think probably C star algebras have too much of a topological flavor. If you look at Gaussian duality, they kind of, I mean, correspond to, or especially at the level of the maps, right? The Gaussian duality, the maps correspond to continuous maps. So I think we probably need something slightly different, a certain class of maybe C star algebras and additional conditions on the morphisms. But roughly to then construct an empirical sampling morphism like this, maybe I can at least indicate what it amounts to, and I'd be curious if anyone has any ideas in either a commutative case or in a non-commutative case. Is probably not much of a difference. So, in C star, well, so then basically the idea would be to try and do something like this, right? But now it should be obviously, since we're in a Heisenberg picture, it should be going the other way. So we want some kind of, let's say, completely positive unital map from some A into its infinite tensor power, right? Okay, and well, what should this map be doing? As long as we just stay at finite n, in that case, it's pretty clear what it should be doing. And basically what we want to do is, so to include A into the nth factor and then average over n. And this is kind of, should be the Heisenberg kind of dual formulation of kind of taking a random element of a finite sequence. And then, well, we should take the limit as the number of factors goes to infinity. So yeah, I think this is what it should be. Something like this at least. We include A into the ith factor, and otherwise take once, and then take the average over these inclusions, and then whatever this limit exactly means. That's the main difficulty, I guess, making this limit precise. Has anyone ever seen anything like this?
How about to consider that instead of the C-star algebra, maybe or the commutative C-star algebra by replacing the non-commutative probability space itself. That is the pair of the C-star algebra and the state. I think you can do such a construction.
Well, that would be in a bit of a, let's say, maybe philosophically somehow different. Because here we want this to be defined independently of any sort of preconceived probability measure. And we should be able to plug in any sequence into here. So yeah, I mean, that sounds interesting. And maybe we could help, but I think it would be something a bit different.
Maybe in this, I understand your idea, but for example, the replacing the not only single state, but some kind of class of states, then maybe it works. How to say that? To take such kind of a operation, maybe it is worth trying to.
Yeah. Okay. Yeah. I mean, I'd be happy to hear more about how. Yeah. Okay. So now in the last few minutes or so, let me maybe say something a bit about what we can do with these empirical sampling morphisms. So and maybe as kind of two of the consequences. Let me write down basically a version of the Definetti theorem again. So we can, in particular, and this is maybe now basically implementing what Fabio's earlier idea, we can use these empirical sampling morphisms to prove the Definetti theorem again, and in particular to prove the uniqueness as well. And now here, so the assumptions are a bit different, and I don't want to spell it out in all detail now, but the main assumption is the empirical sampling the existence of this. And then we prove the Definetti theorem from that, including the construction of the distribution objects. So we're not assuming that these px already exist, but we actually construct them. So this is, we call this then Definetti objects. So under those assumptions, so then there exists px which how do I put this? So with a morphism that already corresponds to the infinite sampling. So an exchangeable L like this. And such that every other exchangeable L uniquely factors through this one. So it's basically what Nico, along the lines of, I think, what Nico had in mind earlier, basically that the px is like the universal object with an exchangeable morphism out of it. And in categorical language, we would call this as saying that it's the equalizer of all the finite permutations on x to the n. So such that every exchangeable p a to the xn uniquely factors through L. And this factoring through is exactly corresponds to the mu from earlier. So meaning that I can write the p as some mu from a to px followed by L. And then as a relatively simple consequence of this, Px turns out to be a distribution object. Okay, so this is kind of circling back to the Definetti theorem. And finally, concerning this statement of convergence of the empirical distribution, I had mentioned that we have also a categorical version of this, and now I can write that down. So this is saying that, let me actually formulate it just in the case for states. So for states, it says that, so meaning just look at a case that is kind of closest to this, where we don't have Markov kernels, but we just have a probability measure mu. And then we basically want to recover the mu by taking infinitely many samples and then looking at their empirical distribution. Okay, so the infinitely many samples means that we're looking at just kind of the infinite product measure. And then we're taking the empirical distribution of these infinitely many. I should make it a little bigger, maybe to indicate that this is the infinite thing. So, well, how do we take the empirical distribution? I mean, we have this empirical sampling thing, but as I had said in introducing this is sort of the counterpart of the empirical distribution of x to the n to px. So this would be our representability or distribution object correspondence, ES sharp. So the deterministic counterpart of ES. And this makes sense. We know this exists because we've proven that distribution objects exist. Okay, and well, then the statement would be, or maybe a first try of what one went down here, and what is indeed something that we can that we've proven is that this is P again. Sorry, no, this is P sharp. Right, this is the actual probability measure P sharp. Now, yeah, do you think these two statements correspond already, or in the sense that if we now take this and instantiate it in Powell-Stock, do we got this thing?
It sort of seem to have the same shape.
Yeah, right. I mean, yes, they're already. They are pretty similar already, but it's actually not quite correct, not quite true yet, because here we have the statement almost surely. Whereas what's going on here is that we're looking at the empirical distribution on average. So here we're kind of averaging and this is also along the lines of what Santiago had asked earlier, that here we're kind of going just down to px and looking at it on average. But we need to take this almost surely into account. And the way to do this is just to say, okay, well, let's just keep track of the sequence that we get here as well. So let's just also use that as an output. And the way to do this is just, well, we copy it here and we kind of, right? So then we got And on the right-hand side, correspondingly, you need to also modify this a little bit. And here, so well, first of all, we still have this infinite sequence. And now, completely independently of this sequence, for the empirical distribution, we have our P sharp. So now this is the actual statement that exactly reproduces this. Right, it's kind of, we're just now we're looking at the joint distribution of the sequence and its empirical distribution. And saying that, well, the empirical distribution is always P sharp, or well, with probability 1, I mean, those distributions, it doesn't matter. But, so with probability 1, it's P sharp, and therefore, in particular, it's independent of the sequence, kind of trivially independent, because it's always P sharp, and so it kind of just diagram falls apart like this, disconnects. Yeah, so this is, and now we can actually also reproduce the law of large numbers, but now maybe I'm a little too out of time to turn into that. But if you know about what an algebra of a monad is, then basically we use algebras of a monad and can compose, take the statement, compose it with the algebra map, and then we basically get this. And so there's another categorical statement of which this literally is an instance. Okay, yeah, I hope it gave at least a bit of a flavor, and yeah, happy to.
Thanks, Tobias.